Lm and n go to the same point.
So you can go back Pappus.
Yeah, Pappus was plagiarizing my computer. But still, Pappus's theorem is a pretty great theorem, and the first theorem that my program tells us is Pappus's theorem. So although I was disappointed that we hadn't beaten Pappus's theorem, I'm still happy that the computer's first fact, the first thing it tells us is Pappus. Let's have it tells us a second theorem on here, which I'm going to skip over. Right, let me go one generation further. So the next generation is going to be making some new lines. Right, okay, and it has, these are all theorems. Every single one of them needs a proof. And probably every single one of them is geometrically interesting, but it's hard work for a human being to decipher all these theorems. So this one caught my attention. I like this theorem, so I'm going to tell you about this one. So this is like its third theorem. So its third theorem says, look at A. This is a really hard thing to read, but what is it? Joined to BACD. It's a pretty complicated looking theorem. BACD we turn into, let's say that's an intersection point. BCAD, that's an intersection point. We make a line, and then we make another line which looks very similar, so I'm going to miss it out. Here's the object of theorem 3. You know, it's up there anyway on the screen. It will be on the video if you want to see this beautiful theorem 3. Okay, and the thing that combinatorial.
So that's a line? Sorry, that's a line that you've.
This is a line, so I should probably put liney brackets around the outside. I'm a bit lazier than the computer, unfortunately. But it has the liney brackets around the outside. Okay, now the thing that caught my attention, the combinatorial count is 20, the geometric count is 5, and 5 is incredibly small. The computer is saying to me, if you start with 5 points, wherever they are, there's an interesting set of 5 lines related to those 5 points. What are those 5 lines? I mean, this is where knowledge of projective geometry is helpful. 5 points in projective geometry. By the way, this line is obviously related to A. It's a line that passes through A, and as well as that, you can read its symmetry group. If you read the symmetry group that's gone off the screen, it's S4 stabilizing A.
So it's a pentagram. It's magic.
But, I mean, it is a magic theorem, but this is what it is. If you've got 5 points, 5 points in projective space determine a unique conic. There's one and only one conic that passes through those 5 points. And it seemed obvious to me, the line related to A must be the tangent to the conic at A. So this is an incidence, a ruler-only construction. Given 5 points, the conic isn't in the picture, given 5 points and a ruler, you can join the right lines and it will give you the tangent to the conic. I must admit, when I first saw this theorem 6 or 7 years ago, I thought that's the tangent to the conic. I never checked it, but since I'm giving a talk, I decided to check it. So I had Geometer's Sketchpad draw out this recipe. Here it is. So there's things like BACD, BCAD are drawn in pale green. The darker green is the line, is this line. The darker blue is that line. The intersection of the dark green and dark blue is that point. I join it to A, and sure enough, it's the tangent to the conic. So in the 19th century, this would have certainly been a nice paper. It probably exists. So given 5 points, ruler only construct the tangent to the conic for 5 points. See, this is the machine's third theorem. Maybe I should prove it for you as well. So let me prove its theorem, because once you know that this is the answer, it's quite easy to prove. So let's have a look at the Pascal line of the hexagon A, B, C, C, D, A. Now, this is slightly peculiar. This is a very funny hexagon. It passes through A twice and C twice. So that means its sides are the tangent at A, the line AB, the line BC, the tangent at C, the line CD, the line DA. You know, again, when you're doing projective geometry, that sort of thing is all natural and well known. If you don't know projective geometry, take my word for it. So you can form the Pascal line for this degenerate hexagon. Now let's think about what it is. Intersections of opposite sides. AB passes through AB intersected with CD, and it passes through BC intersected with DA. And that's what we're seeing here. AB intersected with CD, BC intersected with AD. So this is the Pascal line of the hexagon ABC, CD, A. And this, which is very similar, except we replace D by E, is the Pascal line of the hexagon ABC, CEA. Now, the Pascal line passes through intersection of those two opposite sides, these two opposite sides, and the third pair of opposite sides, the tangent of A and the tangent of C. So this Pascal line passes through the intersection of the tangents at A and C. This Pascal line passes through the intersection of the tangents at A and C. And so the point where they intersect, this point, so this is a recipe for joining A to the intersection points of the tangents at A and C. And the tangent at A passes through here, and there's a proof that it's the tangent at A. And this mysterious point is also on the tangent at C. So if I joined it up to here, I would get another tangent. So there's another theorem that makes sense, possibly new, in which case interesting theorem of geometry. But it's a theorem that the program just told me. Let's run it a little bit.
This is the human generated proof.
This is my proof.
Yeah.
Generator.
So
The computer generated proof would be very different. The computer generated proof, so I have a sneaking suspicion that all of these theorems that it shows us can be proved by Pappus's theorem alone. John and I, when we worked on Pascal's hexagon, all our theorems were proved by Desargues' theorem alone. And so the computer would just search for Pappus configurations and put them together to make a proof. It's proof. Our proof uses human concepts. I mean, humans and computers function differently. And its statement of Pappus's theorem, its statement of here, looks nothing like a nice conceptual human statement. There's still work for a human to do. But the computer produces its things, and
but the discovery does not imply a proof. It's a conjecture only. The discovery program.
What all of the discovery program doesn't prove. I could make it prove. I could build in the old program, and I believe I could make it prove all of these.
Yeah.
But in a sense, I know they're all true. It can't discover a theorem by mistake.
So in the sense, it is proved. Or it's conjecture. Okay.
Yeah, they're not proved, and they're not. This one is proved because I sat down and proved it. Pappus is proved because we saw it's Pappus. Let me take it one generation further. So let's go back to the program. And you can see it goes through these generations very quickly. It produces theorems as fast as you like. Gets a lot of theorems at the next generation. And let me go up towards the top. so many that I don't know if I can find what I want.
But are many of them equivalent? In some
No,
way?
when I calculate the combinatorial group, I don't just feed in what's combinatorially obvious. I feed in all previous information about geometric groups, which are typically bigger. And so the theorems actually are not trivial consequences of previous facts. So at the next level, here is a theorem about a new set of points. Okay, on the last but one line, there's a very complicated looking point. Combinatorial count 15, geometric count 5. Starting from the 5 original points, there's another set of 5 distinguished points that can be produced by a fairly short recipe, although it looks long here. It's relatively speaking short. There's another set of 5 interesting points canonically defined from 5 points in projective space. I've run out of ideas. 5 points, there's a conic, it's got tangents. There's some more geometry, obviously, that produces this other set of 5 points.
What about the pentagons on this diagonal draw? Pentagram.
So you have 5 sides and 5 diagonals. Those are the 10 edges. But the points in the middle are going to be among, but they don't have the full symmetry group S5. They've only got D10. And if you apply the S5, you'll get some more points. You'll get a set of 20 points, I think, if you apply the full symmetry group. So it's not points from a pentagram. I've drawn it out. I would like to know what this is. The new point is up here. It's on the tangent today, but otherwise its geometric significance is beyond my understanding. And this is only a very short way into the list of theorems that computers will generate. And in fact, if I look a bit further down its list at this generation, so let's have a look a tiny bit further, it gets me another thing. Combinatorial count 60, geometric count 5. That's saying this is a very, very strong theorem. The geometry is producing 12, is it 5 into 60 goes 12 unexpected symmetries, which is a lot, more than I've seen anywhere else. And I've drawn that diagram as well. The point is in the middle of nowhere. It's not on any tangents. I've got no idea what that point is, but I suspect that geometrically it's very interesting. 19th century geometers, you can just look at conics, they can look at cubics. I'm sure a 19th century geometer would have a hope of telling us what some of these points are, but I can keep running the program for a few more minutes and it will be getting to theorems that wouldn't make sense, I'm sure, even to 19th century geometers. So maybe I should leave it at that. The thing is, I've got a stupidly simple computer program that churns out statements of theorems, and it's surprising to me how many theorems there are. The early ones we sort of recognize as nice standard theorems that we appreciate in geometry. The later ones, I think they're still good theorems. But
does the number keep growing exponentially? The number at generation n with 5 points?
Yeah, it starts growing very, very fast.
So how many generations did you go?
Not all of it. Well, I went into another 2 or 3 generations and ran out of memory because the program is stupid. I wrote it in an afternoon. It needs to keep track of a lot of groups. I'm a group theorist, and I should have done this better. But to keep track of a group, I just made the set of all its elements, and it stored the set of all its elements. And it does this for the points it's shown you and the points that it's decided were uninteresting. So there are a lot of subgroups of S5 stored in the computer's memory wastefully, and it doesn't get very many steps further. And in some sense, I didn't see a reason to push it very many steps further. I did wonder about recoding it, so it stores groups by naming the group, maybe giving generators, or maybe just, if there aren't that many subgroups of S5, it could store a name of a group and the conjugating elements. And in that case, the program will be able to go very, very far. Time-wise, how does it find the geometric group? It takes 5 random points, it computes actually what these generated objects are, and it just asks, are they the same object? It doesn't do it algebraically at all. It does it in the dumbest possible way. But if you get 5, if you take 5 random points, you're not going to get coincidences. And even if you did, if it accidentally told me that it thinks a line AB is a line AC, it might be unlucky, it might have random points that produce that. It would realize it's made a mistake, because this should be invariant under S5, and if this was the case, it would have to be equal to AD as well. And it runs into trouble when it computes coset representatives and subgroups, and it can tell me something's gone wrong here. Nothing has ever gone wrong, but if the random points are not random enough, unless there was the most unlikely and ridiculous coincidence of
Just out of curiosity, what's the sequence of the number? It goes 0, 0, 2, at the fourth generation. How many did you get?
So you have a sequence.
I can run it again.
Theorems.
So let me run it again. So 1 point and no lines, 1 point and 1 line, 2 points and 1 line. This is cumulative though. The 2 points are all the points it knows about. 2 points and 3 lines, 7 points and 3 lines.
With 2 theorems of generation 4.
Yeah. 7 points and 19 lines, and 4 theorems. 179 points, 19 lines, and I didn't count the theorems. They go off the screen. I could send it to you.
Yeah. I'd like to see it.
Okay, well, I'll send you the sequences.
And I guess the other two also, the number of points and the number of lines.
Yeah, I'll send you all of them.
Yeah.
I feel like stopping.
A beautiful computer experimental talk. As I said, Alan will be glad to answer questions.